Hi viewers, in this video we solve example 8.1 from the book Fluid Mechanics by Sengel. Here is the statement of the example 8.1. Consider the fully developed flow of a glycerin at 40 centigrade through 7 meter long and 4 centimeter diameters horizontal circular pipe. Here it is shown. The flow velocity at the center line is measured to be 6 meters per second. Determine the velocity profile and the pressure difference across these 70-meter long sections of the pipe and the useful pumping power required to maintain this flow. For the same useful pumping power input, determine the percent increase of the flow rate if the pipe is inclined 15 degree downward and the percent decrease if it inclined 15 degree upward. The pump is located outside this pipe section. So here this is the pipe that is, in first case it is horizontal. For that case we need to find the pressure difference and the power input deliver of the pump in order to provide a steady flow rate in this pipe. The length of the pipe is 70 meters and its dia is meters. Okay, so diameters of the pipe is 4 centimeter. To convert into radius, just divide this dia divided by 2, you will get 2 centimeter. So divide with 100 to convert into meters, so it will be 0.02 meter. Next is the length of the pipe. This is L and it is 70 meter long. Okay, so the densities of the glycerin, that is 1252 kg per meter cube. It will be used in the problem, so that's why I'm writing it. Next is the dynamic viscosity. Dynamic viscosity of the glycerins at 40 centigrade, that is 0.3073 kg per meter second. Okay, what we need to find in this statement? So velocity profile, first is to find the velocity profile. Next is to find the pressure difference across this 70 meter long section pipe, and then what is the third one is to find the flow rate, percent increase of flow rate. So flow rate, to find the flow rate when pipe is inclined in upward directions, and find the flow rate when the pipe is inclined in downward direction. Okay, so these are our requirements in these statements, and you will solve it for these requirements. First you need to find the velocity profile. The velocity profile is very easy. So the VR, that is equal to U max. What is U max? It is given 1 minus R square divided by R square. What is U max? U max is the maximum velocity, the center line of the pipe, and it is given, that is 6 meter per second. 6 meter per second. So just put in this formula. So it is 6, 1 minus R divided by R square. So R square divided by this R, it is D by 2. It is 0.02 meter. So it is 0.02. So after simplifications, you will get the velocity profile, that is VR into 6 into 1 minus 1 over 0.02. When you solve on calculators, you will get its value, that is 2500 into r square. And this is our first requirements. Okay, next is to find the pressure difference of this horizontal sections pipe. In order to find this pressure difference, first we need to find the volume flow rate. What is volume flow rate? It is the velocity and area. This is the average velocity. And what is the average velocity? It is the half of the maximum velocity. So what is U max? It is 6 divided by 2. So it will be 3 meter per second. Okay, so VA, V into what is area? That is pi by 4 d square. What is diameter? That is 4 centimeters. To convert into meter is divided with the 100. So it will be equal to 0.04 meter. So now put this in this formula to find the volume flow rate. So volume flow rate is equal to, what is velocity? That is 3 multiplied by 4 by I by 4 into d square, 0.04 square. Then volume flow rate you will get, that is 3.77 multiplied 10 to the power minus 3 meter cube per second. Next we need to find the Reynolds number. So what is Reynolds number? That is equal to rho Vd divided by dynamic viscosity. So what is rho? That is 1252 into velocity, that is 3, dia, that is 0.04 divided by dynamic viscosity, it is 0.3073 kg per meter second. So after simplifications you will get the Reynolds number, and that is 488.9. It is less than 2300. So it means that the flow in this pipe is laminar. It is always that glycerin is very viscous, it's flowing at a very low velocity. So it is obvious that the Reynolds number must be less than 2300, and it comes under the domain of laminar formula. Now to find the fractions coefficients in case of laminar flow, that is 64 divided by Reynolds number. So 64 divided by Reynolds number, that is 488.9. So after solving you will get fractions coefficient, and it is 0.1309. Next to find the head loss. So what is head loss? Head loss is equal to FLV square divided by 2GD. F, that is determined previously, 0.1309 multiply L. L is the length of the pipe, that is 70. V square is the velocity inside the pipe, that is 3 square. 2G is constant, 9.81. Dia 0.04. After solving this you will get the head loss, that is 105.1 meter. So this is much is head loss occur inside the pipe. Now in first case, when the pipe is in the horizontal positions, here from the ground, this is Z1 and this is Z2. So here This is the inlet and here is the outlet. So now by applying the energy equation, that is P1 divided by rho g plus V1 square divided by 2g plus Z1 plus the pump that is provided, so there is no pump between 1 and 2, so just ignore this, the head of the pump. So first I am writing here, now in the next step I will cancel out it. So this, then the head of the pump, if it is provided, is equal to, on the second outlet, the pressure's head P2 divided by rho g, then plus V2 square divided by 2g, and plus Z2 plus head of the turbine if there is, then head loss. So the velocity at the inlet and outlet of the pipe is the same, so it will be cancelled out. There is no pump between 1 and 2, so it will be cancelled out, and there is also no turbine, so it will also be 0. Okay, so shift this P2 to, shift this P1 divided by rho g to that side, so you will get its value, that is P1 divided by rho g minus P2 divided by rho g. So here you will get Z2 minus, so this Z1 will be shifted to that side, that is Z1, and then plus head loss. Okay, so multiply each term with the rho g, so you will get here, that is P1 minus P2 divided by rho g, and it is equal to Z2 minus Z1 plus head loss. So multiply both sides with the rho g. So this will be cancelled out, this, and this P1 minus P2 is the pressure difference. So I can say that pressure difference is equal to rho g into Z2 minus Z1 plus head loss. So in this first case, when the pipe is in the horizontal position, this is Z2 minus Z1. Z2 minus Z1 is equal to 0, and the head loss you will put this value. So the pressure difference in case of the horizontal pipe is equal to rho g. So this is a generic formula. This is, let's say, A. Rho g, and this Z2, Z1 and Z2 are same from the ground level, so that's why it will be 0, and then this rho g will be multiplied with head loss. So what is rho? That is 1252 multiplied by 9.81 multiplied by the head loss is 105.1. So after simplifications you will get the pressure difference Pascal. So to convert into kilopascal, just divide with 1000. These 3 0 will be cancelled out with these 3 zeros, so you will get the pressure difference, that is 1291 kilopascal. Well, next we need to find the work input required from the pump, that is W, and it is equal to the pressure difference of the pipe multiplied by the volume flow rate. So what is pressure difference? That is 1291. Volume flow rate, that is previously determined in the for the horizontal case, it was 3.77 multiplied 10 to the power minus 3. So after simplifications you will get the power input from the pump required, that is this is, let's say, W dot P, and it is 4.87 kilowatt. So now in the next case, the pipe is inclined in upward directions of about 15 degree. In this case, the pipe is inclined in upward directions from that is making a angle 15 degree from the horizontal. So this is the Z1. So this is the Z2. Now the Z1 and Z2 concept has been introduced because the pipe is now in inclined positions. What will be the del Z, that is Z2 minus Z1, and it is L sine angle, that is 15 degree in this case. So I can say that the Z2 minus Z1 value is equal to this L. L is the length of the pipe, that is 70, multiplied by sine 15 degree. So the solving this, you will get its value, that is 18.1 meter. So the pressure difference when the pipe is inclined in upward direction is equal to rho g into the difference of these elevations, that is Z2 minus Z1 plus the head loss as we previously determined. So just put the values in these equations, find the pressure difference for this inclined pipe that is in upward direction. So this is pressure difference up, it is rho, that is 1252, G, that is 9.81, and what is Z2 minus Z1, it is 18.1 plus head loss, that is 105.1. So after simplifications you will get pressures up for this upper inclined pipe, that is 1366 kilopascal almost. Next we need to find the volume flow rate for this pipe that is inclined in upward directions. So you know that the work input from the pump is equal to volume flow rate multiplied by the pressure difference. So now we are finding the volume flow rate for this inclined pipe in upward direction. So here I will write in subscript UP up, and the pressure for it is 1366, and our input for the pump has been determined previously, it is 4.87. So just put in these equations. So 4.87 is equal to volume flow rate, that is our requirement, multiplied by pressures, that is 1366. So just divide both sides with 1366. So this will be cancelled out. So volume flow rate when the pipe is inclined in upward directions, means the pipe is in upward directions inclined, then the volume flow rate will be decreased, and it is 3.57 multiplied by 10 to the power minus 3 meter cube per second. So previously when the pipe was in the horizontal positions, it was denoted by from V dot, and it was 3.77 multiplied 10 to the power minus 3 meter cube per second. So it means that when the pipe is inclined in upward directions, it means that there must be a reduction in volume flow rate. So how much percentage reductions in volume flow rate has been taken place, we need to find its value also. So the percentage decrease is equal to, in volume flow rate, is equal to this original value, that is 3.77 minus the recent value, that is 3.57, divided by 3.57, multiply with 100. So we'll get the decrease in volume flow rate, that is 5.6%. So it means that if the pipe is inclined in upward direction at an angle of 15 degree, volume flow rate will be decreased 5.6%. In the similar case, in the third case, that provided in the statement, if the pipe is inclined in downward directions, so in the downward directions, if the pipe is inclined in downward directions at an angle of 15 degree, then a similar increase of 5.6% occur in the volume flow rate instead of decrease. In this case, then the volume flow rate will increase by 5.6%. So we don't need to calculate this, so it will be obvious that's from our concepts. I hope you understand. If you still have any confusion, you can ask in the comment sections. Thank you so much. If you haven't subscribed to my channel, please subscribe.